Okay, brilliant. So we're going to move on to the final talk of the day from the doctor, I don't know if I pronounce this right, just go for it. And from University of Manchester, so yeah.
Thank you so much. So thank you for still being here and thank you for having me. So I just want to start this talk by acknowledging all of my collaborators who worked with me on these topics, and we still continue working on them. And in particular, actually, can you hear me before I start going? Yeah? Okay. And in particular, I want to acknowledge two former postdocs of mine, so Gunnar Pang and Finn Box. Gunnar is now at UCL, and he's a symptoticist on this problem, and Finn was working on experiments, and he's now joined us in Manchester in physics. So this is really the problem that I want to talk about. So here we have a displacement flow in a very narrow gap that's filled with fluid in between a rigid glass plate and a soft elastic slab that's contained within the mold. And so we're creating a displacement flow by injecting fluid, which can be the same one as already occupying the cell, or a different kind of fluid. And so in principle, here you have up to 3 phases. Okay? So the reason why title is called gas flow displacement under a confined elastic slab is because when Gunnar started doing asymptotics, he decided to put the slab at the top as opposed to what we've done in experiments, which was at the bottom. But essentially, I'll be showing you results assuming that the slab is at the top and all the kind of experimental measurements are kind of reverted accordingly. Okay, so why would you want to study this problem? Well, there's a lot of interest in the literature and to do with multiphase flows and porous media, which is soft, and for example, in this sort of soft granular suspension. There's also more recently sort of creative ways of using sort of well-established flows such as Brotherton bubble to create, for example, soft robotics. I'm coming from Manchester, so I have in my contract I have to mention 2D materials every time I come to a conference. And so there is a spontaneous blistering that happens when you try to make devices from graphene and other 2D materials. And essentially what you're dealing there with often are multiphase flows that can result in these interfacial instabilities below de facto elastic structures. And that's similar to what we've studied over the years, which are these kind of fingering instabilities below elastic sheets, thin elastic sheets. The inspiration for us came from soft microfluidics, and there's been a lot of ideas in the literature for how to use fluid structure interactions to sort of create passive components of microfluidic circuits that don't need external actuation. And so, for example, here there is an example where essentially you have a bit like a cell that what we are considering, except you're dealing with a sort of thin elastic sheet that can deform in response to the flow. And the idea here is to sort of create a microfluidic capacitor that sort of allows a fluid to pass through the circuit, provided you have a particular pressure signal, right? So those are kind of the ideas we're exploiting. Now, what I want to stress about our cells is that unlike a lot of these examples, we actually have volumetrically confined deformations. So our elastic slabs are placed within rigid mold, and we're actually dealing with a quite thick sort of elastic material. So what is the kind of phenomenon that I want to talk about? So here is a top view of my cell, and what we are looking at here is basically the blue is glycerol that we've covered with some ink, so you can see sort of by intensity of the color how deep the layer of the liquid is left inside the cell. And I'm going to be doing the most extreme version of this experiment by injecting some gas into this system. And so if you do that at a sufficiently high rate, then you end up with a Safran-Taylor instability. I'm going to let it run again, sorry, which is not surprising. But what's surprising is that eventually, as you do this experiment, you actually trap the interface inside this cell. And you can see the sort of symptoms of that trapping. I'm just going to run this again. At the edge of the cell, you basically start forming this wide circle, which means that you have basically no liquid left at that edge. And the reason why this circle is formed is because as you were injecting your liquids, you also deformed your elastic slab. You deformed it in such a way as to bulge it near where it's constrained at the edges, and that bulge grew until it kind of touched the opposite rigid wall and shut down the flow. Okay, so that's a phenomenon I want to kind of understand, and in particular in the context of multiphase flow inside the cell. But to begin with, there's too much going on in this experiment, so we've decided to simplify things. And so here is the same experiment where we remove the interface between gas and liquid and just repeat the experiment. And now we're injecting the same kind of liquid that already occupies the cell, except we colored it so you can see how far it gets. And if we run it for long enough, we essentially see that that liquid that we were injecting got trapped inside the cell as well. I should point out that that happens at sufficiently high injection rates. And of course, in this experiment, we're controlling the injection rate. So in order to actually observe trapping, the actual physical mechanism is you inject at the constant injection rate, but then when you kind of, the choking event happens, your pressures inside your system increase enormously, and that stalls your injection, your syringe pump that actually pumps in the liquid at the constant rate. So that's actually what happens in practice, how the stalling happens. Okay, so how do we understand this problem? Well, we can do some modeling as well. And what's important to point out here is that we have a gap-containing liquid, which is very narrow compared to the solid thickness, notated with D here. And there's a number of kind of consequences of that. So in terms of modeling, we can actually use linear elasticity. And those equations we can solve on a fixed solid domain, which makes our lives a lot easier. We have lubrication flow in a narrow gap. So we can do vertically integrated lubrication equations to describe the fluid flow. But of course, we need to couple the two, and that happens through the boundary condition. And it's important to point out that the key coupling happens by vertical deformation and stresses only. We have, because of the scaling in our problem, we have negligible shear stress from fluid onto solid, and we can also neglect horizontal velocity from solid on fluid. Okay, so these are the resulting equations. So at the top there, these are just equations of linear elasticity. The first one is just Hooke's law, essentially. And we have sort of a stress in the solid. We have pressure in the solid. We have vector of displacement in the solid, and that's a shear modulus. And then in here, we have lubrication equations. So the W here is sort of displacement of the surface of the slab. B is the initial gap of the liquid layer. P is the pressure inside the fluid, and mu is the viscosity of the fluid. And then the two talk to each other via this fluid structure interaction boundary condition that says that basically we have stresses and displacements equal at the surface of the slab. So as I already pointed out, extremely important for this problem is the fact that we have a rigid mold that contains our slab. So that means that at the solid boundaries, we have zero displacement of the solid. And then we also need to impose injection and outflow conditions. So essentially, we impose both at the rim of the cell. Okay, so how does the solution to that model look like? Well, here I'm going to just show it in terms of slab deformation. And so what we're looking at essentially is a profile of the gap-containing liquids at this stage. And I'm plotting results for 3 different injection rates. So starting with, let's focus for now on red and green. And so if we look at red and green data, essentially you have several lines there. So this is time evolution of the profile in this experiment. And what I want you to notice is that essentially after a while, at least in cases of green and red data, we kind of get to a steady solution, steady profile in the shape of the cell gap. At the center, we have a bit of vertical displacement, but then for the majority of the cell, essentially there is no displacement vertically. And then at the very edge of the cell, we have this bulging inwards towards kind of the opposite wall that's at that level there. So what's happening here? So basically, we have this solution, and the reason why we're seeing that solution is because what introduces deformation in a solid is the pressure gradient in the liquid. So the pressure gradient that drives the viscous flow results in deformations in the solid, and most of the deformations of solid are actually not vertical, they're mostly horizontal. It's the shearing of the solid. As the solid gets sheared, it happily shears kind of in the majority of the domain, but as it encounters this rigid boundary where it's constrained, it can shear no longer and has to bulge inwards. And that's how this bulge is formed. So it's a boundary layer effect. It's important to also point out that as we get towards higher and higher injection rates, and now let's look at the blue data, we can no longer assume steady profiles. So in fact, blue data, as time evolves, kind of you get the bulge forming, and then that bulge never saturates in height. Instead, you basically, we never attain the steady solution, and our numerics are interrupted when we get extremely close to the opposite wall. Okay, so I already claimed that it's a boundary layer effect, and so we can build a scaling argument based on the size of the boundary layer. And so the boundary layer is actually going to be of the size of the thickness of the slab. And so from the lubrication equations, we can relate the flux there to the pressure gradient. The pressure gradient in the boundary layer needs to be of the order of P divided by the length scale of the boundary layer. And then we can then write down also the pressure that's needed to achieve the elastic deformations, which are of the order of the gap thickness. Because, of course, for us to shut down the flow, we need to have sufficient deformation. From the elasticity that we have, that pressure needs to be to go like this: a shear modulus times the magnitude of deformation divided by the length scale d. So if we balance the pressure, that means that we can predict the scaling for the critical flux that we need to achieve the right kind of deformations in the boundary layer. And then we can test this prediction by doing some experiments and also numerics. So here is the result of our experiment. So here I'm plotting the non-dimensional bulge height. So when the bulge is essentially 1, that's when we have the opposite wall contact. And then for all these discrete points, we have some steady profile inside the cell. And so we've done experiments with all sorts of different cells with different aspect ratios, with the flux with which we injected the liquids, and so on. And we've plotted all of this data as a function of this non-dimensional flux, which is non-dimensionalized using this critical scale that we've estimated with our scaling argument. So you can see that for a while we can attain these steady solutions, but then eventually in the experiment we have a whole bunch of points, these black points, when the system has choked. Okay? Then we can compare that to our numerical data, which is shown with solid lines. And here we're again plotting steady solutions for that model. And you can see that basically there's a whole range of injection fluxes for which there is a steady solution, but they stop existing beyond the critical value of the injection flux. Right? And that's where we would expect to see this choking event. And then if we extract the constants from our numerics, it turns out that the per factor is a magical number 1.4. So 1.4 times this non-dimensional, this flux is when we would expect choking to happen. So let me just summarize. Basically, we have a lubrication flow pressure, that gradient, that drives the lateral solid displacement. The solid encounters the boundary, has nowhere to go, it has to bulge inwards. And as a result of that, it interrupts the flow. And so the reason why we were kind of keen on studying this phenomena is because we thought we could apply that to design a microfluidic fuse inside a microfluidic circuit. And the idea being that if the flux exceeds a critical value, then the flow is interrupted. And so does it work, right? Everything I've showed you so far, if you've looked at the scales, it was on a wrong scale, right? So we can rescale things to go to the microfluidic scale. And actually, we wanted to try it with water as well, because that's typically the working fluid in microfluidics. And we've done a very, very simple experiment whereby we impose the injection flux, and we've measured the outflux, basically. And the two were perfectly in agreement with each other up to a point, and then the critical value of the ejection flux, the outflow, would drop to 0. So that was a sign that our system was working in principle. Okay, so that's the first part of my talk. Now the question is, what about interface, right? And what happens if you now have sort of an interface, and in particular, gas-liquid interface inside such system? And so just to kind of reassure you, previously I've shown you an experiment where the interface fingered. In this version of the experiment, we actually have approximately axisymmetric interface expansion. So we can start by kind of looking at this problem first. And in terms of modeling, almost everything is the same, except now we have lubrication equations that are true. Those are lubrication equations from before, they're true ahead of the bubble tip. Then inside the bubble, we have a pressure that's now constant spatially, but can evolve in time. And then, of course, at the interface, we have additional nonlinearities, as Andrew has told us yesterday. Okay, so that's the problem now. And the question was different. Well, let's consider that model now, again, there is no fingering for the solution, and I also have taken sort of surface tension equal to 0, but adding surface tension doesn't make much difference to what I'm showing you here. So again, we're looking at the gap as it evolves in time, like the profile. And sort of, once again, injection is here. This is the rim of the cell. And I'm also actually this time plotting the position of the bubble tip as well as time evolves. So unlike before, we no longer have steady solutions. And we will never have steady solutions in this problem because, of course, we're injecting at the constant injection rate. And so we need to, in order to maintain kind of mass balance, that means the interface constantly has to slow down, right? As it radially expands. So, but ahead of the interface, that profile is very similar to what we had before, essentially the same profile. Behind, however, we have approximately constant deformation, at least in our direction, and that's because we have spatially constant pressure. It's just a constant pressure inside the bubble that we're imposing. And another observation is that over time, that kind of deformation there relaxes, right? So if we look here versus there, central deflection returns to 0, and that's because we need less pressure difference to drive the same flux through the system, right? So pressure over time decays, and equivalently, this goes back to 0. That results in, at the interface, the deformation of the slab generally being pulled apart, because on one hand, you're going back to 0 here, on the other hand, you still have pressure gradient at the other end, right? So that pulls apart your solution. And you can also do some very interesting maths here, and actually there is a nice traveling wave solution if you're far away from your boundaries. It's similar to, we had a talk yesterday about the plate dripping on the plate, essentially the same type of maths you can do here as well. Okay, so if your interface is sufficiently far away from this bulge, the bulge is still in the boundary, so it's not going to be affected by the interface. But as soon as the interface approaches the bulge, so I should put this up. But as soon as the interface approaches the bulge, then that boundary layer solution is affected by the interface, right? And the effect of having this interface closed is it actually reduces the amplitude of your bulging. So just to convince you that that's the case, here I'm showing sort of the maximum deflection in the cell as well as at the center of the gap for both the gas and the liquid injection. So let's focus on liquid injection for now. So in the liquid, if we look at any of the dashed lines, we're basically at the center, deflection would increase and then saturate as we get to the steady solution. And then in the bulge region, depending on how quickly or at what volume flux we inject liquids, we would either saturate to some constant height or we would choke, right, for the green and the blue data. Now, if we go to gas injection, so this is now solid lines. So the solid lines in the center, they increase and then decay towards 1, right? Because, again, we relax in the center. But then at the boundary, if we manage to choke long before the interface has reached the boundary, then basically the lines follow exactly the same predictions as in the liquid case, right? But then we also have scenarios whereby initially the sort of bulge grows in amplitude and then interface is too close, so it relaxes backwards. Right? And we have situations whereby we've choked in the liquid injection during liquid injection, but we've didn't choke during the gas injection. Okay, so in principle, we have a mechanism which delays the choking, delays the trapping inside the cell when we have two-phase flow. So what happens in the experiments? Just very quick note, in the experiments are more complicated than my model. So to begin with, if you want quantitative agreement with experiments, you really need to worry about things such as films left behind the interface as the bubble propagates, and we can correct for those. There is by modifying kinematic and dynamic boundary conditions in a sort of semi-ad hoc way. If we do that, then there is a quantitative agreement between experiments and numerics. And here, this is just plotting the interface position as a function of time, and this is just sort of overlaying the two together. But actually, experiments are a lot more complicated. In principle, interface fingers, because for most of these choking events, you really need to go to high enough injection rates, at which point interface will naturally finger due to Safman-Taylor instability. And of course, another thing is when you increase the rate with which you inject gas, then you have to remember that gas is actually compressible, right? And that also happens. And the consequence of gas compressibility for us is that we have non-constant volumetric flux. Even though we think we impose particular volume flux, in practice we don't have a constant volume flux throughout. And that has its own complications. We can actually extract the volume flux we have in the experiments through different methods. We applied them all and they kind of agree with each other. We actually have done very precise measurements of how much liquid we have inside the cell at all times, so we can differentiate that data, get the flux. We've measured the pressure throughout our experiments, and we can do thermodynamics and relate the two. We have traveling wave solution, and again, we can integrate that to get the variations in time of the volumetric flux. Essentially, all three agree with each other. These are kind of different regimes in which we've checked that they agree. But ultimately, we have a non-constant volume flux in time that we can then impose in our theory to see what the effect of fingering is. And then we can ask our question, is having fingers at interface making tropic more difficult or easier than having no fingers? That's the question I'm asking. Okay, so here's a whole bunch of experiments that we've done and kind of all the different regimes. And it's kind of phase diagram. And in this direction, we're changing how deep the cell is, so how narrow the gap is initially. In this direction, we're changing how quickly we're injecting liquids. So if you look at the bottom figures, for example, we go from having approximately axisymmetric interface to having fingered interface. What's important to notice in this direction is that as we change the parameters, we go from having wide fingers to having much more narrow fingers. And that's something you would expect for Huffman-Taylor instability. However, what really surprised us is the choking efficiency. So if we focus on this corner here, what we found is that having fingers actually suppresses choking. So in other words, if the interface has fingered, then they happily escape, whereas escapes the cell, whereas the analogous sort of circular bubble would not. And that's because, when you think about the mechanism that we have, that's because the fingers are faster in approaching the rim of the cell than our axisymmetric bubble would be. Right? And they're faster, therefore all these arguments about fingers being closer work. Okay? However, what really surprised us is that in this corner here, the opposite was true. So fingering actually was, or interfaces with fingers were more effective, or our cell was more effective at trapping interfaces with fingers. Okay? And actually, it was more effective at trapping them than even the case of a single-phase injection, which is shown with these dashed lines here. Right? So that was really surprising. So we had kind of a very counterintuitive result that fingering, on one hand, can promote sort of choking, but on the other hand, can suppress it. So very briefly, in my last slide, what is the mechanism for this? Okay, so as already said, a bubble has a negligible effect on this boundary layer if it's far away from the rim. However, when you have viscous fingering, then that means that part of your interface get to the rim very, very quickly, right? And that means that essentially you are, when you're shearing that part of that soft cell that you're shearing, that drives the bulging, is in principle smaller, right? That mechanism acts on the length scale that's associated with the thickness of the slab, as I was arguing in my boundary layer argument. However, when we have fingering, we also don't have uniform volume flux everywhere, right? We have localization. There is a local flux ahead of the fingers is actually stronger than the mean flux, right? And that means that basically just ahead of the fingers, provided they're wide enough, so this is the length scale associated with the width of the fingers, we can actually exceed that critical flux that we need to in order to choke, right? So that led to observation that actually wider fingers, because they're effective at localizing flux, are good. They promote choking. And narrower fingers are actually the opposite, right? There is this opposite mechanism that they actually escape the cells. Okay? So that's it. Just in the last minute, I want to conclude by saying that hopefully I've showed you a interesting new phenomenon the consequence of flow structure interaction, I think it has a lot of potential applications, maybe. So one of the ideas that we're currently sort of considering is whether or not this phenomenon works in different geometries, the idea being to integrate it more effectively into microfluidic circuits. So here is a cylindrical geometry where basically we are, this is a soft, so we're within the cylinder, most of the cylinder is filled with a soft material. In the middle, we have a little channel, and we are actually operating on a scale which is more similar to microfluidics, right? So the actual kind of width of the channel is in the order of hundreds of microns. And our preliminary sort of results suggest that we can get choking-like deformation. So this is a sort of a view of that channel before we start injecting liquids. We inject, in this case, from that side to that side. And after we start injecting, we do see indeed this non-uniform deformation kind of narrowing towards the end of the region of kind of flow propagation. And then another, so this is by the way with thin box. And another project that we have on a similar topic is with Chris McMinn, and this is to do with the internal choking. So now here, what we have is an empty cell, or cell filled with air, and we're filling it with a viscous fluid. And if I let this play, initially there is a very kind of nice uniform bubble expanding, but then you probably have noticed the moment when there is this lighter gray region around the bubble appearing. So that means that there is a choking just ahead of the interface that kind of then kind of expanded, and eventually the original liquid started kind of propagating into that region where there is kind of a adhesion between a soft slab and a rigid wall, and form these beautiful sort of fingering patterns. So okay, I'm going to stop there. Thank you.
Thank you. About the choking itself, I'm not sure, is it a final time singularity where the two interfaces touch each other? And maybe a similar question, what happens after? Because after there is no more flow that creates the choking, so it should relax, or is there...
So it's a good question. I think after physics changes completely, right? And so I think at the moment the models that we use don't have that physics in them. I think when we're still at the stage with here we're at the stage of doing experiments, and ideally we would like EPSRC to give us some money to actually understand what's happening beyond the touchdown point. I can tell you that experimentally, in the first version of the experiment, as I said, what happens in practice, there is a massive spike in the pressure, and it's just our syringe pumps cannot overcome it, so they just stall, and therefore you are kind of in that position where you're touching the opposite wall, you stay there, because you're not pumping anything in anymore. Adhesion is somehow helping you, right?
And the final dynamics is a final time singularity?
So we haven't explored that far. We interrupted our simulations where we got really, really close to the opposite wall. So our criteria for choking is basically we get within a couple of % of the distance from the opposite wall, and then we stopped. It probably is. I don't know. Yeah.
Okay. Any other questions?
You try experiment that impose pressure instead of impose flow rate?
Yeah,
and,
it's a very good question. And they're not interchangeable, the two. So if we've tried it, it still works. And I suspect that adhesion actually helps in that scenario. But if you were to just do the modeling that we've done, it turns out that there is always a steady solution if you control pressure instead of the flux. But however, what happens is that the bulging gets extremely close to the opposite wall. And in that length scale, probably other physics takes over, right? And you probably have, the PDMS that we use, for example, is the Silgard 527, which is very tacky and never completely clean. The surfaces are really, it's impossible to make it flat, right? And so I suspect that there is a little bit of imperfection. You're so close that it just adheres to the opposite wall. But model certainly always computes the steady, we always get the steady profile in that case. So it's not the same.
Okay, final question if anybody has any questions. If not, I think that's it. So let's thank both speakers and thank you so